Look up at the night sky on a clear evening and find our moon, that pale, luminous companion hanging in the darkness above you. From here, even with the naked eye, you can see the scars etched across its surface. Dark patches that ancient civilizations called seas, lighter highlands that rise like mountain ranges, and if you look closely enough on a clear night when the moon is full, the shadows of ancient wounds, circular depressions that mark where cosmic violence once struck with unimaginable force. Our moon is a battered world, a celestial body that has been struck again and again by cosmic projectiles, by asteroids and meteorites that left craters so immense, so profound, that they transformed its very face and remain visible across nearly 400,000 kilometers of space. But these impacts, these scars, these wounds carved into the lunar surface, were not random acts of violence spread evenly across billions of years of slow, gradual bombardment. They came in a surge, a deluge, an apocalyptic storm of rock and ice that swept through the inner solar system in what may have been the most catastrophic, most transformative period in our planetary history. Scientists call this event the Late Heavy Bombardment, and it happened roughly 4 billion years ago, during a window of time that was cosmologically brief, perhaps only a few 100 million years, yet geologically devastating beyond measure. This was not a slow siege, not a gradual accumulation of impacts over eons. It was a blitzkrieg from space, a concentrated assault that may have reshaped not just the moon, but every terrestrial planet in the inner solar system. The consequences of this bombardment were profound and far-reaching, rippling forward through time to touch every aspect of the solar system we inhabit today. It may have delivered the very ingredients that made life on Earth possible, the water that fills our oceans, the organic molecules that became the building blocks of the first living cells. It may have shaped the destiny of every terrestrial planet in our solar system, determining which worlds would become havens for life and which would remain barren wastelands. And it raises a question that seems almost impossible to answer, a puzzle that has occupied planetary scientists for decades. If the moon was so savagely scarred during this period, its surface transformed into a cratered wasteland, how did Earth survive? The answer is both terrifying and beautiful, both simple and profoundly complex. Earth did not avoid the bombardment. It did not hide behind some cosmic shield or escape the fury of the asteroid storm. It was struck just as violently, just as relentlessly, with impacts that must have been even more devastating than those that scarred the moon. But unlike the moon, which is a dead world with no atmosphere, no geological activity, no way to heal its wounds, Earth was able to transform that destruction into creation, turning cosmic chaos into the blue, life-bearing world we know today. The very forces that could have sterilized our planet, that could have boiled away any nascent oceans and destroyed any possibility of life, instead became the mechanism by which life became possible. To understand how this happened, how destruction became creation, we must journey back in time, 4 billion years into the past, to an era when our solar system was still young, still violent, still finding its equilibrium after the turbulent process of planetary formation. We must explore the forces that sent asteroids hurtling toward the inner planets, the gravitational dynamics of the outer solar system that disrupted the peaceful orbits of countless small bodies. We must understand the chemistry that turned barren rock into fertile ground, the processes by which simple elements combined into complex molecules capable of self-replication. And we must appreciate the extraordinary timing that allowed water and organic molecules to arrive at precisely the right moment, at precisely the right stage in Earth's geological evolution, to spark the origins of life. This is the story of the Late Heavy Bombardment, a story that begins not on Earth or even on the moon, but in the outer reaches of the solar system, where giant planets danced through the darkness and their movements sent shockwaves rippling through the asteroid belt. It is a story of planetary migration, of gravitational resonance, of chaos and order emerging from the primal cloud of gas and dust that gave birth to our sun and all the worlds that circle it. It is a story that connects the largest structures in our solar system, the gas giants Jupiter and Saturn, to the smallest building blocks of life, the amino acids and nucleotides that form proteins and DNA. And it is a story that reminds us of how contingent, how improbable, how extraordinarily fortunate our existence truly is. When the Apollo missions returned from the lunar surface in the late 1960s and early 1970s, they carried with them more than dust and stories of walking on another world. They brought back fragments of the moon itself, hundreds of kilograms of rock that had been untouched for billions of years, preserved in the airless, weatherless void of space where no wind erodes, no water dissolves, no plants or animals disturb the ancient stones. These rocks told a story that scientists had not expected, a story encoded in the very atoms that make up the lunar samples. Among the rocks were pieces of impact melt, stones that had been superheated by meteorite strikes, liquefied into magma by the tremendous energy of high-velocity collisions, and then slowly cooled back into solid form over thousands of years. This was not unusual in itself. The moon is covered with impact craters, thousands upon thousands of them ranging in size from tiny pits barely visible under a microscope to enormous basins hundreds of kilometers across. Scientists expected to find evidence of collisions. The moon's appearance from Earth makes that obvious. But what surprised them, what fundamentally changed our understanding of the early solar system, was the timing of these impacts. The Apollo astronauts had collected samples from different regions and craters across the near side of the moon, from the flat plains of the Maria to the heavily cratered highlands, from the rim of ancient impact basins to the floors of younger craters. Yet when these rocks were analyzed using radiometric dating techniques, methods that measure the decay of radioactive isotopes to determine how long ago the rocks solidified, almost all of them showed ages clustering around the same narrow window, between 4.1 and 3.8 billion years ago. Very few samples showed evidence of impacts older than this period, and relatively few showed impacts significantly younger. The implication was startling, revolutionary even. For some reason, during this roughly 300 million year window, there had been an abnormal spike in meteorite impacts, a surge of activity that stood out against the background of bombardment that must have occurred during the formation of the moon and the gradual decline of impacts as the solar system swept up its debris. The moon had been subjected to an intense and concentrated bombardment, a cosmic storm that left its surface permanently scarred with the largest craters we see today. This hypothesis became known as the Late Heavy Bombardment, and it has sparked decades of scientific debate, controversy, and investigation. Not everyone agrees that it happened the way the theory suggests. Some scientists argue that the clustering of ages could be the result of sampling bias, that the Apollo missions only visited a few locations, all on the near side of the moon, all in regions that may have been influenced by the same large impact events. Perhaps, they suggest, the astronauts inadvertently collected rocks from overlapping crater systems, from debris fields thrown out by the same giant impacts, which would artificially create the appearance of a clustered bombardment period. Others suggest that the dating techniques themselves might be influenced by factors we do not yet fully understand, that some geological process, perhaps the heat from later impacts or the slow accumulation of radiation damage, could be resetting the radiometric clocks in ways that create artificial patterns in the data. Such is the nature of science when working with limited evidence, when entire theories must be built on just a few hundred kilograms of rock from a world where billions of tons of material lie scattered across millions of square kilometers. We have only been to the moon a handful of times. Only 6 missions successfully landed astronauts on the surface, and the samples we brought back represent a tiny fraction of the moon's composition, a minuscule window into 4.5 billion years of history. But if the Late Heavy Bombardment did happen as originally theorized, if the clustering of ages is real and not an artifact of sampling or measurement, it raises a profound question that cuts to the heart of planetary formation and solar system dynamics. What could have caused such a sudden, violent surge of impacts 4 billion years ago, 500 million years after the planets themselves had already formed? To answer that question, we must go back even further in time, to the very beginning of our solar system, to the moment when there was nothing but darkness and dust. 4.6 billion years ago, in a quiet corner of the Milky Way galaxy, there was no Earth, no moon, no planets at all. There was no sun burning bright at the center of a system of worlds. There was only a vast rotating cloud of gas and dust, a nebula spinning slowly in the darkness of space, a remnant of previous generations of stars that had lived and died and scattered their atoms into the void. At the center of this cloud, gravity was at work, the fundamental force that governs the cosmos, pulling matter inward, compressing it, concentrating the mass of the cloud into an ever denser, ever hotter core. As matter fell inward, it heated up, not through any chemical burning, but simply through the compression of atoms squeezed into smaller and smaller volumes. The temperature rose from just a few degrees above absolute zero to hundreds, then thousands, then tens of thousands of degrees. The pressure mounted, the density increased, and at some critical threshold, when the conditions became extreme enough, something remarkable happened. The hydrogen atoms at the core, squeezed so tightly together that their electron clouds touched, began to fuse into helium. Nuclear fusion ignited, releasing tremendous amounts of energy in the form of light and heat. A star was born. Our sun blazed into existence, and its light illuminated the swirling disk of material that surrounded it, a flat, rotating disk of gas and dust that astronomers call the protoplanetary disk. This disk, stretching billions of kilometers from the infant sun, was the raw material from which everything in our solar system would eventually form: the rocky planets near the sun, the gas giants in the outer reaches, the asteroid belt between Mars and Jupiter, the icy bodies of the Kuiper belt beyond Neptune, and all the countless smaller objects that populate the space between. The composition of this protoplanetary disk was, in essence, the composition of the cloud from which it formed, which in turn was the legacy of all the stars that had come before. It was composed primarily of hydrogen and helium, the most abundant elements in the universe, the primordial elements created in the Big Bang itself. But mixed in with this hydrogen and helium were heavier elements, elements forged in the nuclear furnaces of earlier stars: carbon and oxygen, silicon and iron, magnesium and aluminum, and trace amounts of nearly every element in the periodic table. These elements had been created through nuclear fusion in the cores of massive stars and then scattered into space when those stars died, either through gentle stellar winds or through violent supernova explosions that briefly outshone entire galaxies. The dust grains in the protoplanetary disk, the tiny solid particles suspended in the gas, were made of these heavier elements. There were grains of silicate minerals, compounds of silicon and oxygen with various metals mixed in. There were grains of metallic iron and nickel. There were grains of carbon in the form of graphite or even more exotic organic compounds. And in the colder regions of the disk, far from the heat of the young sun, there were grains of ice, frozen water, frozen carbon dioxide, frozen methane, and ammonia. As the disk rotated, these dust grains began to collide, sticking together through a combination of electrostatic forces and the simple stickiness of ice and organic compounds, forming larger and larger clumps. This process, known as accretion, started slowly. The first clumps were barely larger than the grains themselves, perhaps a millimeter or a centimeter across. But once a clump reached a certain size, it began to exert its own gravitational pull, weak at first, but gradually strengthening as more material was added. Gravity accelerated the process, pulling in nearby grains and smaller clumps, growing the object faster and faster in a runaway process. Over time, measured in thousands and then millions of years, the disk transformed from a smooth cloud of dust into a collection of discrete objects called planetesimals, the building blocks of planets. These planetesimals ranged in size from small boulders to objects hundreds of kilometers across, miniature worlds in their own right, and they continued to collide, to merge, to grow. In the inner solar system, closer to the sun where temperatures were high, the environment was hostile to volatile compounds. Water could not condense into ice. Methane and ammonia remained as gases. Only rocky, metallic materials, substances with high melting points, could survive in solid form. This is why the inner planets, Mercury, Venus, Earth, and Mars, are all rocky worlds, composed primarily of silicate rock and iron, with little to no hydrogen or helium, despite those elements being the most abundant in the universe. The gas simply could not be captured by the small, rocky planetesimals in the hot inner disk. The process of forming the terrestrial planets happened remarkably quickly by geological standards, though it would have seemed impossibly slow by human measures. Within just 100 million years, a time span that seems vast to us, but is barely a moment in cosmic history, the inner solar system had coalesced from a cloud of dust into a handful of rocky worlds. But this process was not gentle or gradual. It was violent, chaotic, a cosmic demolition derby. During this chaotic period, planetesimals collided with each other in impacts that released tremendous amounts of energy, enough to vaporize rock and melt entire worlds. Some collisions destroyed both objects, shattering them into countless smaller fragments that scattered back into the disk. Others resulted in the two objects merging, creating a larger planetesimal from the debris. The largest planetesimals, through a combination of fortunate positioning and gravitational dominance, grew faster than their neighbors, sweeping up material from wider and wider orbits, eventually becoming the cores of the terrestrial planets. One of these collisions, occurring roughly 4.5 billion years ago, was particularly significant for the story of Earth and the Moon. A Mars-sized object, an embryonic planet that never quite made it to full planetary status, was on a collision course with the early Earth. This object, sometimes called Theia, after the Greek Titan, who was the mother of the moon goddess Selene, struck the proto-Earth with unimaginable force. The impact was so violent that it vaporized a huge portion of both bodies, superheating rock into a plasma of dissociated atoms. The force of the collision sent a massive plume of vaporized rock, molten magma, and solid debris flying into space, escaping the gravity of the merged planet and forming a ring around Earth. This ring, similar in some ways to the rings of Saturn but far more massive and substantial, was unstable. The material in the ring collided and coalesced, and over a surprisingly short period, perhaps only a few thousand years, gravity pulled the ring together into a single object. The moon was born from the remnants of that catastrophic collision, a child of violence that has orbited our planet ever since. This giant impact explains many of the moon's unusual properties: why it is so large relative to Earth, why it has such a small iron core compared to Earth, why the rocks brought back by Apollo have an isotopic composition so similar to Earth's mantle, and why the moon is slowly receding from Earth as tidal forces transfer angular momentum from our planet to its satellite. By 4.5 billion years ago, the process of planetary accretion in the inner solar system was largely complete. Most of the material had been swept up into the 4 terrestrial planets, or ejected from the inner solar system entirely. Some debris remained, scattered between the planetary orbits, and collisions continued, but the frequency of impacts was declining. The inner solar system was settling down, cooling off, becoming a more stable place. If the bombardment of the moon had simply been a continuation of this accretion process, a gradual winding down of the collisions that built the planets, we would expect to see a smooth decline in impact rates over time. There would be many impacts early on, when debris was abundant, and fewer impacts as time passed, and the material was swept up. But that is not what the lunar rock samples suggest. Instead, they indicate a sudden spike in impacts 4.1 billion years ago, 500 million years after the planets had already formed, 500 million years after the initial frenzy of planetary accretion should have ended. Something had disrupted the stability of the inner solar system, disturbing objects that had been in stable orbits for hundreds of millions of years, sending a new wave of asteroids and comets hurtling toward the terrestrial planets. To understand what that something was, we must turn our attention outward, beyond the asteroid belt, beyond the orbit of Mars, to the giant planets of the outer solar system. Jupiter, the king of planets, the colossus that dominates the gravitational landscape of our solar system, holds the key to this mystery. Jupiter is enormous, a gas giant with more than 2.5 times the mass of all the other planets combined. It contains 318 times as much mass as Earth, and yet it is still far too small to ignite nuclear fusion and become a star. Jupiter formed early in the history of the solar system, accreting from the vast reserves of gas and ice in the outer protoplanetary disk, in the region where temperatures were low enough for water and other volatiles to condense into ice. This ice, combined with rock and metal, formed the core of Jupiter, and once that core reached a critical mass, somewhere between 10 and 15 times the mass of Earth, it became massive enough to capture huge amounts of hydrogen and helium directly from the surrounding gas disk. Jupiter grew rapidly, ballooning to its current size within just a few million years of the formation of the solar system. Along with Saturn, the second largest planet, which formed in a similar manner, Jupiter quickly dominated the gravitational landscape of the outer solar system. But here's the crucial point. Jupiter and Saturn did not always orbit where they do today. In fact, their movements through the early solar system, their migration inward and then outward through the protoplanetary disk, may have been the trigger for the Late Heavy Bombardment. When Jupiter first formed, the protoplanetary disk was still full of gas, a thick atmosphere of hydrogen and helium that had not yet been blown away by the solar wind or dissipated into space. This gas created drag, a subtle but persistent force that acted on Jupiter as it orbited the Sun. Just as a satellite orbiting Earth will slowly spiral downward if it encounters the thin upper atmosphere, Jupiter experienced a drag force from the gas in the protoplanetary disk. This drag caused Jupiter to lose angular momentum, and as it lost angular momentum, it spiraled inward toward the Sun. Over hundreds of thousands of years, Jupiter migrated from its original orbit in the outer solar system to a position much closer to the Sun, perhaps as close as 1.5 astronomical units, roughly where Mars orbits today. This inward migration had profound and far-reaching consequences for the structure of the solar system. As Jupiter moved, its immense gravity disrupted the orbits of countless smaller objects, asteroids that had formed in stable orbits, comets in the outer reaches of the solar system, planetesimals that had not yet been incorporated into larger bodies. Many of these objects were flung out of the solar system entirely, ejected into interstellar space by close gravitational encounters with the giant planet. Others were pushed into highly elliptical orbits that brought them dangerously close to the inner planets, crossing the orbits of Mars, Earth, Venus, and even Mercury. The inner solar system, which had been relatively calm for hundreds of millions of years as the planets finished forming and the remaining debris was slowly swept up, was suddenly flooded with new projectiles, with asteroids and comets on collision courses with the terrestrial worlds. But Jupiter's migration did not continue indefinitely, and this is where Saturn enters the story. As Saturn formed and grew, it too began to spiral inward, dragged by the same gas that was pulling Jupiter toward the Sun. Saturn was smaller and formed later than Jupiter, so its migration began later, but once it started moving inward, it gradually caught up to Jupiter in a gravitational sense. Eventually, the two giant planets became gravitationally linked, locked into what is known as an orbital resonance. In this configuration, the orbital period of Saturn became related to the orbital period of Jupiter by a simple ratio. Specifically, they entered a 2-to-1 resonance, meaning that for every one orbit Jupiter completed, Saturn completed exactly 2 orbits. This resonance is stable and self-reinforcing, and it has a remarkable effect. The combined gravitational influence of Jupiter and Saturn in resonance creates a powerful outward force, a kind of gravitational recoil that counteracted the drag of the gas disk. Jupiter's inward migration halted, and then, astonishingly, reversed. The giant planet began to move back outward, pushed by the gravitational dance with Saturn, returning to the orbit we see today at roughly 5.2 astronomical units from the Sun. This grand migration, sometimes called the grand tack hypothesis, because Jupiter's path resembles the tacking maneuver of a sailboat changing direction, had a dramatic effect on the asteroid belt and, by extension, on the Late Heavy Bombardment. The asteroid belt, located between the orbits of Mars and Jupiter, is a region that today contains millions of small, rocky, and metallic bodies ranging in size from dust grains to objects hundreds of kilometers across. The largest asteroid, Ceres, is nearly 1,000 kilometers in diameter and massive enough to be classified as a dwarf planet. But the total mass of all the asteroids combined is less than 5% of the mass of the Moon, a surprisingly small amount given the vast region they occupy. This is because the asteroid belt was heavily depleted during the early history of the solar system, and Jupiter's migration was responsible. As Jupiter swept through the region between Mars and Jupiter during its inward and then outward migration, it scattered the asteroids that had formed there. Some asteroids were sent inward toward the terrestrial planets. Others were flung outward into the outer solar system or beyond. A few lucky ones remained in stable orbits, and these are the asteroids we see today. The asteroid belt, which may once have contained enough material to form another planet, was reduced to a fraction of its original mass, and most of that material was redistributed throughout the solar system. The asteroids that were sent toward the inner solar system during Jupiter's migration came in two distinct types, a fact that would later prove crucial for the development of life on Earth. The first type, known as S-type asteroids, are stony asteroids composed primarily of silicate minerals and metallic iron. They formed in the inner regions of the asteroid belt, closer to the Sun, where temperatures were high enough to vaporize volatile compounds like water. These asteroids are relatively dry, containing little to no water or organic compounds. They are rocky, metallic, and in composition similar to the terrestrial planets. The second type, known as C-type asteroids, are carbonaceous asteroids, rich in carbon compounds, and, critically, water ice. These asteroids formed in the outer regions of the asteroid belt and beyond, in the region where temperatures were low enough for water and other volatiles to condense into solid form. C-type asteroids are among the most ancient objects in the solar system, primitive remnants of the protoplanetary disk that have remained largely unchanged for billions of years. Their dark surfaces, coated with carbon-rich organic compounds, make them among the darkest objects in the solar system, reflecting less than 10% of the sunlight that strikes them. When Jupiter's migration disrupted the asteroid belt, both types of asteroids were sent streaming toward the inner planets in what would become the Late Heavy Bombardment. And when they arrived, they transformed Earth forever. To understand how Earth was affected by the Late Heavy Bombardment, we must first understand what our planet was like 4 billion years ago, at the beginning of the Archean Eon. Earth had formed roughly 500 million years earlier, coalescing from the rocky debris of the inner solar system through the violent process of planetesimal collisions. In its earliest days, during the Hadean Eon, Earth was a molten sphere, heated by the energy of countless collisions and by the decay of radioactive elements in its interior. The surface was an ocean of liquid magma, glowing red and orange in the darkness of space, radiating heat into the void. The atmosphere, if it can even be called that, was a thin envelope of vaporized rock and metal, along with gases released from the interior through volcanic activity. Over millions of years, this heat gradually dissipated. The surface began to cool, and as it cooled, a thin, solid crust formed on top of the magma ocean. This crust, known as the lithosphere, floated on the still molten mantle below, like the skin on cooling pudding. At first, this crust was thin and unstable, frequently breaking apart and sinking back into the magma as new crust formed above it. But gradually, As more heat was radiated into space, the crust thickened and stabilized, forming a more permanent barrier between the molten interior and the cold vacuum of space. By 4 billion years ago, Earth had developed a stable, if still geologically active, crust. The lithosphere was fractured into many small tectonic plates that shifted and collided, driven by convection currents in the mantle below, by the slow churning of hot rock rising from the deep interior and cooler rock sinking back down. Volcanic activity was intense during this period, far more active than it is today, with lava frequently erupting through cracks in the crust and spreading across the surface in vast flows. The rocks that formed this early crust were primarily basalt, dark gray to black in color, a volcanic rock similar to the lava that erupts from volcanoes in places like Hawaii and Iceland today. Basalt is rich in iron and magnesium, which gives it its dark color, and it forms when molten rock from the mantle cools relatively quickly at the surface. The early Earth would have looked like a dark volcanic wasteland, with black or gray rocks covering most of the surface and frequent eruptions lighting up the sky with fountains of glowing lava. The atmosphere of early Earth was nothing like the air we breathe now. It was thick and toxic, a choking mixture of gases that would be lethal to any modern organism. The primary components were likely carbon dioxide, water vapor, nitrogen, and smaller amounts of methane, ammonia, and sulfur compounds. There was no oxygen, or at most only trace amounts produced by the breakdown of water vapor by ultraviolet radiation from the sun. Without oxygen, there was no ozone layer, and the surface of Earth was bathed in harsh ultraviolet radiation that would have quickly destroyed any complex organic molecules. The sky would have been a dull, hazy orange or gray, very different from the blue we know today, illuminated by the young sun and punctuated by the bright streaks of incoming meteors that burned up in the thick atmosphere. The surface temperature was much higher than it is today, perhaps as high as 70 to 90 degrees Celsius in some regions, hot enough to make the environment extremely hostile, but not so hot that liquid water could not exist. The interior of the planet was significantly hotter than it is today as well, with temperatures in the upper mantle reaching around 1600 degrees Celsius, hot enough to keep rock in a plastic, slowly flowing state. This heat came from two sources: the residual heat left over from the accretion process, from all the kinetic energy of the planetesimals that had collided to form Earth, and the decay of radioactive elements like uranium, thorium, and potassium, which were far more abundant in the early Earth than they are now. This internal heat drove the geological processes that shaped the surface, from volcanic eruptions to the slow movement of tectonic plates. In this hot, active environment, something remarkable was beginning to happen deep inside the planet. The heavier elements in Earth's interior were sinking toward the core in a process known as differentiation. When Earth first formed, it was likely a relatively homogeneous mixture of all the elements that had been present in the protoplanetary disk, with iron, nickel, silicon, oxygen, magnesium, and other elements mixed together throughout the volume of the planet. But iron and nickel are much denser than the silicate minerals that make up most of Earth's rock, and in the molten or semi-molten state of the early Earth, gravity caused these heavier elements to sink slowly toward the center. This process was accelerated by large impacts, which melted portions of the planet and allowed the iron to flow more freely. Over tens of millions of years, Earth separated into layers: a dense iron, nickel core at the center, a silicate mantle surrounding the core, and a thin crust of lighter silicate minerals at the surface. This differentiation had profound implications for Earth's future. The metallic core, once it became large enough and hot enough, began to generate a magnetic field through the dynamo effect, the movement of electrically conductive liquid iron creating electrical currents that in turn generate magnetic fields. This magnetic field extends far into space, creating the magnetosphere that protects Earth from the solar wind and prevents our atmosphere from being stripped away as happened on Mars. The differentiation also meant that many of the heavier, rarer elements, such as gold, platinum, iridium, osmium, and uranium, were concentrated in the core, sinking along with the iron and becoming largely inaccessible at the surface. The crust and upper mantle became enriched in lighter elements like silicon, aluminum, calcium, sodium, and potassium, while depleted in the heavy metals. This depletion would have been nearly complete if not for one crucial event: the Late Heavy Bombardment. As the bombardment began, roughly 4.1 billion years ago, Earth was subjected to a relentless barrage of impacts. Asteroids ranging in size from small boulders just a few meters across to objects hundreds of kilometers in diameter slammed into the surface at speeds of tens of kilometers per second. Each impact released enormous amounts of energy that had been stored as kinetic energy in the motion of the asteroid and was converted into heat, shock waves, and the physical disruption of rock. A typical asteroid impact can release energy equivalent to millions or even billions of nuclear weapons, depending on the size and speed of the impactor. The heat generated by these impacts was intense enough to vaporize rock, turning solid stone into glowing plasma in the blink of an eye. The shock waves from the impacts propagated through the crust, fracturing rock, triggering earthquakes, and sometimes even penetrating deep enough to disrupt the mantle and trigger massive volcanic eruptions on the opposite side of the planet. The impacts excavated vast craters, throwing enormous amounts of debris into the atmosphere and even into space. Some of this debris fell back to Earth within hours or days, creating a rain of molten rock that covered wide areas around the impact site. Other debris was thrown into orbit, forming temporary rings around the planet before eventually falling back to the surface. The largest impacts, those caused by asteroids tens or hundreds of kilometers across, were global catastrophes. They released enough energy to melt portions of the crust, creating seas of molten lava that could cover areas the size of continents. The dust and vapor thrown into the atmosphere by these impacts would have blocked out the sun for years or even decades, plunging the surface into darkness and causing temperatures to plummet. When the dust finally settled and the sun returned, the surface would have been transformed, with vast areas covered in fresh lava flows and the atmosphere enriched with new gases released from the vaporized rock and from the impactors themselves. The bombardment was so intense that the surface of Earth was constantly being reshaped, melted, and reformed. Some scientists have estimated that during the peak of the Late Heavy Bombardment, large impacts may have occurred every few 100,000 years, and smaller impacts would have been even more frequent, perhaps one every few decades or centuries. But unlike the Moon, which retained its craters as permanent scars visible even today, Earth's surface was geologically active in ways the Moon was not, and never has been. The tectonic plates shifted and collided, one plate sliding beneath another in a process called subduction, carrying old crust down into the mantle where it melted and was recycled. New crust was created at mid-ocean ridges, where mantle material rose to the surface and solidified. Volcanic activity constantly resurfaced areas of the crust, covering old craters with new lava flows. Erosion, once liquid water became abundant, wore down the raised rims of craters and filled the depressions with sediment. This constant recycling meant that the craters created during the Late Heavy Bombardment were eventually erased from the geological record, their traces lost to the processes that continue to reshape our planet today. No rocks from the very beginning of the Late Heavy Bombardment survive on Earth. The oldest known rocks, small samples found in places like the Jack Hills of Western Australia, the Acasta gneiss in northwestern Canada, and the Isua greenstone belt in southwestern Greenland, date to around 4 billion years ago, roughly the end of the Late Heavy Bombardment. Everything older has been destroyed, buried deep in the crust, and metamorphosed into unrecognizable forms, or subducted into the mantle and melted back into magma. The only direct evidence we have for the bombardment comes from the Moon, which has preserved a pristine record of this violent period precisely because it lacks the geological processes that erase such evidence on Earth. But while the craters themselves have vanished from Earth's surface, the asteroids left behind something far more valuable: something that would prove essential for the development of life. The raw materials, the chemical elements and compounds that make up living organisms. As the asteroids rained down onto Earth during the Late Heavy Bombardment, they brought with them a treasure trove of elements and molecules. The stony S-type asteroids, composed primarily of silicate minerals and metal, delivered valuable elements that had been depleted from Earth's surface during the differentiation process. These included precious metals like gold, silver, platinum, palladium, iridium, and osmium, which have a strong affinity for iron and had sunk into the core along with the iron during Earth's formation. These elements, known as siderophile or iron-loving elements, are relatively rare in Earth's crust compared to their abundance in the solar system as a whole, and this depletion was one of the early pieces of evidence for core formation. But when meteorites and asteroids struck Earth after differentiation was complete, they delivered these elements to the surface in a form that could be incorporated into the crust rather than sinking to the core. It is now believed that many of the valuable metal deposits we mine today, from the gold veins of the Witwatersrand Basin in South Africa to the platinum deposits of the Bushveld complex, from the copper porphyry deposits of the Andes Mountains to the nickel deposits of Sudbury, Canada, may have originated at least in part from this extraterrestrial delivery during the Late Heavy Bombardment and the subsequent slower bombardment that continued afterward. But even more important than precious metals, more important than gold or platinum or any other rare element, was the arrival of water. The carbonaceous C-type asteroids formed in the cold outer reaches of the asteroid belt, where temperatures were low enough for water to freeze, contained vast amounts of water ice mixed with rock and organic compounds. These asteroids are thought to be up to 20% water by mass, an enormous reservoir of H2O locked in the frozen bodies that drifted through the early solar system. When these icy asteroids struck Earth during the Late Heavy Bombardment, they delivered their cargo of water to the surface. Some of this water, particularly that in smaller asteroids or in the outer layers of larger ones, vaporized on impact, the tremendous heat of the collision turning ice into steam in a fraction of a second. This water vapor was added to the atmosphere, thickening it and increasing the greenhouse effect, which helped to keep the surface warm even as the sun was fainter than it is today. But not all the water vaporized. Large asteroids, particularly those that struck at relatively shallow angles or landed in regions that were already covered with water or sediment, could deliver water to the surface in a more or less intact form. The ice in the interior of these asteroids, insulated by the outer layers of rock, could survive the impact and be released as the asteroid fragmented and the heat dissipated. Over time, over millions of impacts spanning hundreds of millions of years, the amount of water delivered to Earth's surface grew from scattered puddles to lakes, from lakes to seas, and from seas to oceans. As the surface cooled and the bombardment gradually declined in intensity, the water vapor in the atmosphere began to condense, a process that may have taken millions of years. The sky darkened as the thick clouds formed, and then the rain began. It may have rained continuously for thousands or even millions of years, a planetary deluge that filled the low-lying basins created by the asteroid impacts and by the tectonic activity of the young planet. Slowly, imperceptibly at first, but then with gathering momentum, the oceans began to form. The timing of this water delivery was crucial, perhaps the most important factor in determining whether Earth would become a living world or remain barren like Venus or Mars. If the asteroids carrying water had arrived earlier, during the Hadean Eon when Earth's surface was still molten or semi-molten, and the planet was still experiencing frequent giant impacts, the water would have simply evaporated back into space. The early Earth lacked a strong enough magnetic field to protect its atmosphere from the solar wind, and without an atmosphere to provide pressure, liquid water could not exist on the surface. Any water vapor in the atmosphere would have been broken down by ultraviolet radiation into hydrogen and oxygen, and the light hydrogen atoms would have escaped into space while the oxygen reacted with rocks, or was blown away by the solar wind. Mars, smaller than Earth and with a weaker gravitational field, likely suffered this fate. Mars probably received water during the same late heavy bombardment that brought water to Earth, and there is abundant evidence that Mars once had liquid water on its surface, from ancient river valleys to vast plains that may have been ocean floors. But Mars could not hold on to its water. Without the geological activity to recycle the crust and regenerate the atmosphere, without a strong magnetic field to shield the atmosphere from the solar wind, Mars gradually lost its water over hundreds of millions or billions of years. The atmosphere thinned, the temperature dropped, and Mars transformed from a potentially habitable world into the cold, dry desert we see today. Earth, by contrast, was at the perfect stage of development to receive and retain the water delivered by the asteroids during the late heavy bombardment. The lithosphere had cooled and solidified enough to support a stable crust, providing a solid foundation on which liquid water could pool and persist. The interior of the planet remained hot and active, driving volcanic activity that continuously released gases into the atmosphere, replenishing the atmosphere and maintaining a thick enough gas envelope to provide pressure and a greenhouse effect. The core had differentiated and was generating a magnetic field strong enough to deflect most of the solar wind, protecting the atmosphere from being stripped away. And the temperature at the surface, kept warm by the thick atmosphere and by the residual heat from ongoing impacts, was in the right range for liquid water to exist, not so cold that everything froze solid, not so hot that water could only exist as vapor. By the end of the late heavy bombardment, around 3.8 billion years ago, Earth had been transformed from a barren, volcanic world into a planet with vast oceans covering perhaps 70 to 80% of the surface. A thick atmosphere composed primarily of nitrogen and carbon dioxide with water vapor and trace amounts of other gases, and a surface rich in the elements necessary for life. The oceans that formed during and shortly after the late heavy bombardment were not like the oceans we know today. They were warmer, with surface temperatures perhaps as high as 50 to 70 degrees Celsius in many regions, hot enough that life as we know it today would struggle to survive except in the cooler deep waters. The water itself was different in composition. It was acidic, with a pH perhaps as low as 5 or 6, due to the high concentrations of dissolved carbon dioxide in the atmosphere which formed carbonic acid when it dissolved in water. The oceans contained high concentrations of dissolved iron, giving the water a greenish or brownish tint, rather than the blue we associate with seawater today. There was no oxygen dissolved in the water, making the oceans anoxic, unable to support most forms of complex life that exist today. But these oceans, harsh and alien as they would seem to us, were exactly what was needed for life to begin. But water alone is not enough to create life. Life, at least life as we understand it, life as it exists on Earth, requires complex organic molecules, amino acids, the building blocks of proteins, nucleotides, the building blocks of DNA and RNA, lipids, the fatty molecules that form cell membranes, and sugars, which provide energy and structural support. These molecules are all based on carbon chemistry, on the unique ability of carbon atoms to form long chains and complex structures by bonding with other carbon atoms and with atoms of hydrogen, oxygen, nitrogen, phosphorus, and sulfur. For decades, scientists debated how these organic molecules could have formed on the early Earth. The classic experiment by Stanley Miller and Harold Urey in 1953 seemed to provide an answer. Miller and Urey created a sealed apparatus containing water, methane, ammonia, and hydrogen, gases that were thought at the time to make up Earth's early atmosphere. They subjected this mixture to electrical sparks to simulate lightning and to heat to simulate volcanic activity. After running the experiment for a week, they analyzed the contents and found that several amino acids had formed, along with other organic compounds. This seemed to demonstrate that the building blocks of life could form spontaneously under the conditions of the early Earth, that life did not require any special intervention or implausible coincidence, just the right chemistry and energy. However, later research suggested that the early Earth's atmosphere was probably not as rich in hydrogen, as Miller and Urey had assumed. A more likely composition would have been dominated by carbon dioxide and nitrogen, with smaller amounts of water vapor and perhaps methane and ammonia. Experiments using these more realistic atmospheric compositions have been less successful at producing organic molecules, though they can still form under certain conditions, particularly in the presence of volcanic gases or with the energy from ultraviolet radiation or impacts. But there was another possible source for the organic molecules needed for life, a source that became more plausible with the discovery that such molecules exist in space and have been delivered to Earth by meteorites. We now know, from decades of meteorite research and from recent missions to asteroids and comets, that many of the essential building blocks of life exist in space and have existed there since the formation of the solar system. The 5 nucleotides that make up DNA and RNA, adenine, guanine, cytosine, thymine, and uracil, have all been detected in carbonaceous chondrite meteorites, ancient stones that are samples of the most primitive asteroids in the solar system. These nucleotides were not created recently or contaminated from Earth. They are indigenous to the meteorites, formed in space billions of years ago. Amino acids, the building blocks of proteins, have also been found in abundance in carbonaceous chondrites. More than 70 different amino acids have been identified in the Murchison meteorite, which fell in Australia in 1969, and many of these amino acids do not exist in terrestrial biology, proving that they formed in space rather than being contamination from Earth. Even more complex organic molecules have been discovered. Lipids, the fatty molecules that form the membranes of cells, have been detected in meteorites. Sugars, including ribose, the 5-carbon sugar that forms the backbone of RNA, have been found. Polycyclic aromatic hydrocarbons, complex ring structures of carbon and hydrogen that are common in space, are abundant in carbonaceous meteorites. The question then becomes not whether organic molecules could have formed on Earth, but whether they needed to, or whether they were simply delivered from space during the Late Heavy Bombardment. The answer is probably both. Some organic molecules likely formed on Earth through chemical reactions driven by lightning, volcanic heat, ultraviolet radiation, or the energy of impacts. But many others were likely delivered from space, carried in by the same carbonaceous asteroids that brought water. The challenge is understanding how these delicate molecules could survive the violent impact of an asteroid striking Earth's surface. Today, when a small meteorite enters Earth's atmosphere, it experiences tremendous friction as it plows through the air at speeds of tens of kilometers per second. This friction heats the surface of the meteorite to temperatures of thousands of degrees, often causing the object to glow white-hot and creating the bright streak we call a meteor or shooting star. Most small meteorites burn up completely before reaching the ground, vaporized by the heat. Any organic molecules they contained would be destroyed long before the meteorite landed. But during the Late Heavy Bombardment, the asteroids were much larger than the typical meteorites that fall today. A large asteroid, hundreds of meters or even kilometers across, would not burn up in the atmosphere. It would be slowed slightly by atmospheric drag, but its enormous mass and momentum would carry it through the atmosphere in just a few seconds, barely enough time for the outer surface to heat up significantly. The asteroid would punch through the atmosphere and strike the surface with tremendous force, and while the collision would generate enormous heat, this heat would be concentrated primarily on the outer layers of the asteroid and the immediate impact site. The interior of the asteroid, insulated by the surrounding rock and ice, could remain relatively cool, protected from the worst effects of the impact heating. If that interior contained ice and organic molecules frozen within the ice or adsorbed onto the surfaces of mineral grains, they could be delivered to the surface largely intact. The asteroid would shatter on impact, fragmenting into countless pieces ranging from boulders to dust, and these fragments would be scattered across the impact site and the surrounding region. Some of the fragments, particularly those from the interior of the asteroid, would contain unaltered organic material ready to be incorporated into the chemistry of the early Earth. In this way, the late heavy bombardment may have seeded Earth with the raw materials for life, delivering not just water, but also the complex organic compounds needed to start the chemical processes that would eventually lead to the first living cells. The evidence for this scenario is compelling and continues to grow stronger as we analyze more meteorites and study more asteroids. The isotopic composition of organic molecules in meteorites shows clear differences from terrestrial organic molecules, proving an extraterrestrial origin. The diversity of organic compounds found in carbonaceous chondrites is remarkable, including molecules that are rare or absent in modern biological systems, but that could have been important in the origin of life. And the sheer abundance of organic material in these meteorites, often several percent of the total mass, suggests that the delivery of organic molecules during the late heavy bombardment could have been substantial, potentially far more than could have been produced by early Earth chemistry alone. The oldest fossils on Earth, microscopic structures preserved in ancient rocks that may represent the remains of ancient bacteria, or archaea, date to around 3.5 billion years ago, preserved in rocks from the Pilbara region of Western Australia and the Barberton Greenstone Belt in South Africa. These fossils, though their biological origin has been debated, appear to show cellular structures, sometimes arranged in chains or filaments suggestive of bacterial colonies. Chemical signatures in even older rocks, specifically the ratios of carbon isotopes in graphite inclusions in rocks from Greenland and Canada, suggest that life may have existed even earlier, perhaps as far back as 3.8 billion years ago, right at the boundary between the Hadean and Archean eons, immediately after the late heavy bombardment ended. If this is true, if life really did emerge on Earth almost immediately after the bombardment ceased, it implies that life arose as soon as conditions became stable enough to support it. As soon as the frequency of large impacts declined to the point where emerging life would not be immediately destroyed by the next impact. This timing is not a coincidence. It suggests that the late heavy bombardment created the conditions necessary for life, that without the bombardment, life might not have arisen at all, or might have been delayed by billions of years. The bombardment delivered water, creating the oceans that served as the solvent and medium for the chemistry of life. It delivered organic molecules, providing ready-made building blocks that could be assembled into more complex structures. It delivered energy in the form of heat from impacts, which could have driven the chemical reactions needed to assemble those building blocks into functional molecules and eventually into the first primitive cells. And it delivered minerals and metals, including elements like iron, magnesium, phosphorus, and molybdenum, which are essential cofactors in many biological enzymes, and which may have catalyzed the early reactions that led to life. The impacts themselves may have created favorable environments for the origin of life. When an asteroid struck the ocean, it excavated a deep crater on the seafloor, fracturing the rock and allowing seawater to circulate deep into the crust. This created hydrothermal systems, regions where hot water from the interior mixed with cold seawater, creating steep temperature and chemical gradients. These gradients could drive chemical reactions, concentrating molecules and providing energy for synthesis. Hydrothermal vents, both the high-temperature black smokers and the lower-temperature alkaline vents, are considered by many scientists to be among the most likely sites for the origin of life on Earth. And the late heavy bombardment would have created countless such sites across the seafloor. In this sense, the bombardment was not just a period of destruction, but a period of creation, a violent but necessary step in the transformation of Earth from a lifeless rock into a living world, a crucible in which the raw materials of life were delivered, concentrated, and assembled into the first organisms. But to truly understand the late heavy bombardment and its role in shaping not just Earth, but the entire inner solar system, we must return once again to the Moon, the silent witness that has preserved the evidence that Earth has lost. The Moon is the key to unlocking the secrets of this period, because unlike Earth, where geological processes have erased the craters and recycled the rocks, the Moon has remained largely unchanged for billions of years, a frozen snapshot of the early solar system. The surface of the moon is covered with craters, layer upon layer of overlapping impact scars that record billions of years of bombardment. Some of these craters are small, just a few meters or even centimeters across, created by micrometeorites no larger than grains of sand. Others are enormous, the largest visible from Earth with the naked eye. The largest impact structures on the moon, known as impact basins, are truly colossal features. The South Pole Aitken Basin, located on the far side of the moon and therefore never visible from Earth, is the largest confirmed impact basin on the moon, and one of the largest in the entire solar system. It is approximately 2,500 kilometers in diameter and up to 8 kilometers deep, a scar so vast that it would stretch from New York to Denver if it were on Earth. This basin was created by an asteroid perhaps 200 kilometers across, striking the moon with such force that it excavated material from deep within the lunar crust and possibly even from the mantle beneath. On the near side of the moon, the side we always see from Earth, the largest basins are filled with dark basaltic lava, creating the features called maria or seas, because early astronomers thought they might be bodies of water. The largest of these maria, such as Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis, and Mare Crisium, are hundreds to over 1,000 kilometers across. These basins were created by massive impacts during the Late Heavy Bombardment, impacts so powerful that they fractured the lunar crust, allowing molten rock from the mantle to flow up and fill the basins over millions of years. The lava that filled these basins, similar to the lava that erupts from volcanoes on Earth, but with slightly different composition due to the moon's different chemistry, solidified into smooth plains of dark rock. These dark plains contrast sharply with the brighter, heavily cratered highlands surrounding them. And this contrast is what creates the familiar pattern we see when we look at the full moon, the pattern that different cultures have interpreted as a face, a rabbit, or various other shapes. The reason the moon has preserved this record so well, the reason its surface is still scarred by impacts that occurred billions of years ago, is that the moon lacks the geological processes that erase such features on Earth. The moon has no plate tectonics. Its interior cooled long ago, and without the convective circulation of hot rock that drives plate movement on Earth, the moon's crust is a single solid shell that does not recycle or renew itself. The moon has no volcanic activity in the present day. The last volcanic eruptions on the moon occurred around 1 billion years ago, and even those were minor compared to the vast outpourings of lava that filled the maria during the first billion years of lunar history. The moon has no atmosphere, and therefore no wind, no rain, no weather to erode the surface. The only process that modifies the lunar surface today is the slow, gradual accumulation of more impacts, smaller meteorites slowly grinding the rock into finer and finer powder over billions of years, creating the layer of regolith, lunar soil, that covers the entire surface. This regolith, typically several meters deep, is composed of pulverized rock, tiny glass beads created by the heat of impacts, and occasional fragments of meteorites themselves. Once a crater forms on the moon, it remains essentially unchanged except for the slow degradation caused by subsequent smaller impacts. The sharp rim of a fresh crater gradually becomes more rounded as meteorites chip away at it. The interior of the crater slowly fills with regolith shaken loose by nearby impacts, but the crater itself persists, visible for billions of years. By studying the moon's surface, by mapping the craters and determining their ages, scientists can reconstruct the history of impacts in the inner solar system and, by extension, the history of impacts on Earth and the other terrestrial planets. The Apollo missions provided the first direct evidence for the Late Heavy Bombardment by bringing back samples of impact melt and breccia, rocks formed by impacts, from various locations on the moon. When these samples were dated using radiometric techniques, which measure the ratios of radioactive isotopes and their decay products to determine how long ago the rock solidified, they revealed a surprising pattern. The samples from the Apollo 11 mission, which landed in Mare Tranquillitatis, the Sea of Tranquility, were dated to around 3.7 billion years ago. The samples from Apollo 12, which landed in Oceanus Procellarum, the ocean of storms, showed similar ages. The samples from Apollo 14, which landed in the Fra Mauro Formation, debris thrown out from the impact that created Mare Imbrium, were dated to around 3.9 billion years ago. The samples from Apollo 15, which explored the Hadley Apennine region near the rim of Mare Imbrium, also showed ages around 3.9 billion years. The samples from Apollo 16, which landed in the highlands and collected some of the oldest rocks returned from the Moon, showed a range of ages, but with many samples clustering around 3.9 to 4.1 billion years ago. And the samples from Apollo 17, the last Apollo mission, which landed in the Taurus Littrow Valley, found rocks with ages spanning the same general range. Most of the large impact basins on the Moon, when dated by the ages of the rocks associated with them, appear to have formed within this relatively narrow window between roughly 4.1 and 3.7 billion years ago. This clustering of ages was unexpected and led to the hypothesis of the Late Heavy Bombardment, a sudden spike in impact rates occurring hundreds of millions of years after the Moon and planets had formed. However, it is important to note that the evidence is not as clear-cut as this simple narrative might suggest. As analytical techniques have improved, and as scientists have subjected the Apollo samples to more detailed study, some complications have emerged. Not all samples fit neatly into the 4.1 to 3.8 billion year window. Some rocks show evidence of impacts both earlier and later than this period. Some scientists have argued that the apparent clustering might be an artifact of sampling bias, noting that all the Apollo missions landed on the near side of the Moon and that many of the samples may be related to just one or two very large impacts. Particularly, the impact that created Mare Imbrium, which threw out enormous amounts of debris that were later collected by multiple Apollo missions. If most of the dated samples are actually ejecta from the same few large impacts, then the clustering of ages would not indicate a sudden surge in impact rates across the entire Moon, but rather would simply reflect the ages of those particular impacts. This alternative hypothesis, sometimes called the declining bombardment model, suggests that the impact rate simply declined gradually after the formation of the planets, with no distinct spike or late heavy bombardment period. According to this view, the Moon was continuously bombarded from its formation until a few billion years ago, with the impact rate steadily decreasing over time as the solar system's supply of debris was gradually exhausted. The apparent clustering of ages around 4 billion years ago is, in this interpretation, simply because we have not sampled enough of the Moon to see the full range of impact ages, and because the largest impacts, which are the most likely to produce samples that can be dated, happen to occur during that time period. Resolving this debate, determining whether the late heavy bombardment was a real event or an artifact of limited sampling, will require more data, and that means more missions to the Moon to collect samples from new locations. The Apollo missions visited only 6 locations, all on the near side, all in a relatively narrow band of latitudes not far from the equator. The far side of the Moon, which is never visible from Earth due to tidal locking, remains almost entirely unexplored by human missions, though it has been photographed by orbiting spacecraft and even visited by robotic landers in recent years. The polar regions, which may contain deposits of water ice in permanently shadowed craters, have never been visited by humans. Future missions, such as NASA's Artemis program, which aims to return astronauts to the Moon in the coming years, will collect samples from new locations, including the South Polar region. These missions will employ more advanced dating techniques and will search for other types of evidence that can help determine the timing and intensity of the bombardment. They will also study the composition of different impact materials to learn more about the types of asteroids and comets that struck the Moon and Earth. Even if the bombardment turns out to have been more gradual than originally thought, even if the clustering of ages proves to be partly or wholly due to sampling bias, the basic conclusion remains unchanged. The Moon, and by extension Earth, and all the terrestrial planets, were subjected to intense bombardment during the first few 100 million years of their existence. This bombardment, whether it came in a sudden surge or as a gradual decline from the even more intense collisions of the planet-forming era, played a critical role in delivering water and organic materials to Earth's surface and in setting the stage for the origin of life. On Earth itself, the direct evidence for the late heavy bombardment has been largely erased by 4 billion years of geological activity. The craters that must have covered the surface, craters even larger than those on the Moon because Earth's stronger gravity would attract more impactors, are gone, buried under layers of sediment, erased by erosion, or destroyed by the movement of tectonic plates and volcanic activity. There are impact craters on Earth today, and geologists have identified nearly 200 confirmed impact structures ranging from small, simple bowl-shaped craters to enormous complex structures hundreds of kilometers across. But these are relatively recent features by geological standards. The Barringer crater in Arizona, one of the best preserved impact craters on Earth, a nearly perfectly circular bowl about 1.2 kilometers in diameter and 170 meters deep, was created only about 50,000 years ago when an iron meteorite, roughly 50 meters across, struck the desert at a speed of around 12 kilometers per second. The Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico, and identified only through geophysical surveys and drill cores, was created 66 million years ago when an asteroid roughly 10 kilometers across struck Earth, causing the mass extinction that killed the dinosaurs and many other species. The Vredefort crater in South Africa and the Sudbury Basin in Canada are among the oldest confirmed impact structures on Earth, both dating to around 2 billion years ago, but even these ancient scars are far younger than the late heavy bombardment. The craters from the late heavy bombardment, if any survive at all, would be so deeply buried, so heavily metamorphosed, so thoroughly destroyed by billions of years of geological processes, that they would be unrecognizable as impact structures. Yet there are indirect clues that the bombardment occurred, subtle signatures in the geological and chemical record. The presence of certain elements in Earth's crust provides one line of evidence. Elements like iridium, osmium, platinum, and gold are known as highly siderophile elements, meaning they have a very strong affinity for metallic iron. During Earth's differentiation, when the iron and nickel sank to form the core, these siderophile elements should have gone with them, leaving the crust and mantle depleted. And indeed, the concentrations of these elements in Earth's mantle and crust are very low compared to their abundance in the Sun and in primitive meteorites, but they are not completely absent. There is far more of these elements in Earth's crust than there should be if all of them had sunk to the core during differentiation. The most widely accepted explanation is that these elements were delivered to Earth's surface after differentiation was complete, added by the late heavy bombardment and subsequent meteorite impacts. The isotopic composition of Earth's water also provides a clue to its origin. Water molecules come in different isotopic forms, depending on whether the hydrogen atoms are the common light isotope, protium, or the heavier isotope, deuterium. The ratio of deuterium to protium, often denoted as D-H ratio, varies depending on where and how the water formed. Water in Earth's oceans has a specific D-H ratio, and by comparing this ratio to the D-H ratios measured in various extraterrestrial sources, scientists can infer where Earth's water came from. Comets, which form in the cold outer reaches of the solar system beyond Neptune, tend to have D-H ratios that are significantly higher than Earth's oceans, suggesting that comets were not the primary source of Earth's water. Carbonaceous asteroids, particularly those from the outer asteroid belt, have D-H ratios that closely match Earth's oceans, suggesting that these asteroids were indeed the primary source of our water. This isotopic evidence supports the idea that much of Earth's water was delivered by asteroids during the late heavy bombardment and subsequent impacts,